In this video, we're going to explore the origins of polyatomic ions, and this might help you understand where they come from and therefore remember them. So most of them in our list come from what are called oxyacids. Oxyacids are just acids with oxygen in them. An acid is a chemical. Anytime a chemical releases a proton, it's considered an acid. And a proton gets released when hydrogen is covalently bonded to something, and that something says, I'm not sharing that electron with you anymore, get out. And so it boots out the hydrogen nucleus, which is just a proton. So you'll see the proton represented as H+, and that's just a proton that's been kicked off of a chemical from before. So if we look at our first chemical, or our first polyatomic ion we ever discussed, was nitrate, right? So we got an NO3 with a minus plus a proton. And that came from a chemical called nitric acid, so HNO3. So nitric acid had one proton to donate. So I'm actually going to draw it out so that you can actually see what it looks like. So there's your nitrogen, and we got 3 oxygens kicking around here. 1, 2, 3 in this molecule, and then we've got a little hydrogen that's hanging out on that one. Okay, so that first oxygen, and you can draw them any which way, that doesn't matter really. So what's going to happen here is that you still got the nitrogen in the middle, but this oxygen has ripped off the electron and kicked out that proton. And that proton's got to find somewhere to go live. And I'm going to talk about where that thing goes a little bit later on. And to represent that, I'm just going to show that hydrogen floating around like that. Now we can look at chloric acid. Chloric acid has a similar structure, but a different chemical formula. So say, HClO3, and that's going to dissociate into the chlorate ion, ClO, 3 minus, plus a proton, H plus, and let's draw this little dude here. So again, similar setup. You got 3 oxygens, so we're going to draw them in a triangular formation like this. And this is kind of actually what the molecule looks like. It's not a bad representation. So there's a little hydrogen hanging out there. And that oxygen says, you know what, I think I want to keep your electron. And you can go. Find somewhere else to live. Poor little proton. And when that proton lands on something else, it's a bit of a celebration. And that's where the corrosive nature of that comes into, is the energy release when that proton actually binds to its new location. So there you go. All right, so there's your chlorate ion. And in a way, it's useful to draw these out fully. And again, we can reduce it to simple particles, but for the purpose of this, we're going to look at them fully, and hopefully you'll see the pattern. Now, let's go through our chemical formulas, right? Bicarbonate, we know that one from the chart, HCO3 minus, and we know carbonate is CO3 minus 2. And these two actually are kind of crazy cousins of each other, because they derive from this substance called carbonic acid. And in fact, carbonic acid is in our blood, and it helps to maintain the pH of our blood. Our blood can't get too acidic or too basic. If it does, we get in trouble. And that's not a good thing. All right, so let's draw the sucker out, because, well, I like doodling, so it's a good deal. All right, so if we look at, we'll start from the acid this time. So I'm going to draw the carbon in the center. We call that the central atom. It's pretty highfalutin science language there. Again, because there's 3 oxygens around that central atom, we're going to draw it in a triangular formation, because they want to kind of stay away from each other as much as possible. And 2 of these 3 are going to have the hydrogens hooked up to them. And don't worry about the Lewis dot drawings. We can ignore that for now. So round one, one of the hydrogens gets booted off, and it doesn't matter which oxygen you draw it coming off of. It could be this first one here, or it could have been this one. Doesn't matter. So HCO3 plus that proton, is now floating around in solution. And it's, again, got to go find a home. We'll talk about where that sucker ends up later. And we said that this is in water, so that's going to come into play. All right, so if bicarbonate, well, it's also got a proton itself, and an extra proton there, and it could dissociate to form carbonate. So that one already went, and that then goes like that. It's my fantastic artistic drawings here. High-level graphics. But I'm hoping you see the pattern now. So, as those acids release those protons, well, they become anions, polyatomic anions. And they're polyatomic because they came from molecules where everything's shared. All right, let's jump down to sulfate. Now, sulfate's interesting, and we'll look at our chemical formulas on those guys. So we know that's SO4 minus 2 plus a proton. There's your proton. Bisulfate, HSO4 minus. And hopefully you're starting to see the pattern so that you would deduce that the formula for sulfuric acid, which we find in batteries, is H2SO4. And we can start again with the acid. Now, since it's 4 oxygens, I'm going to put my sulfur in the middle, and I'm just going to put 4 around here. There we go. We got a hydrogen there and a hydrogen on that oxygen. So, round 1. Now keep in mind, there's 2 hydrogens there, so we can actually get through 2 dissociations. And that first dissociation is where the bicarbonate, or sorry, bisulfate I should say, or hydrogen sulfate, it's also called, comes from HSO4. So we got 1, 2, 3, and the fourth one there is going to be my negative one, because that's the one that let go of that proton, booted that proton out actually. And we still have a hydrogen though on this oxygen here. So that can do another dissociation, which is going to result in having a sulfate ion with 2 oxygens that are negatively charged now. One there, and then that second proton has been released. All right, now phosphoric acid is interesting because, well, we got that phosphate. So let's take a look at phosphate formula. Now, we remember that it's PO4 negative 3 plus a proton. So we can deduce, and kind of looking backwards, that the PO4 with the negative 3, that must mean that there must have been 3 hydrogens attached to 3 of the 4 oxygens. And indeed, that's the case. So we're going to work this case backwards. There's your phosphate, and there's a proton there that got kicked off, that last one. Prior to this, we had what we're going to call hydrogen phosphate. Moving backwards, right? So there's your purple for your phosphate. 1, 2. Negative there. Negative there. And there's going to be a proton, or sorry, a hydrogen connected to that one. All right. I don't know, I'm working backwards, so let's go from the beginning, and we'll see it all merge together. So phosphoric acid, well, the formula for that, actually, let's get our formula here. HPO4 negative 2 plus a proton. So when HPO4 negative 2 releases it, that's when we get our phosphate, and that final proton being released. All right, so dihydrogen phosphate, so H2PO4 minus plus a proton. So then that means that our original formula for phosphoric acid is H3PO4. And if you look at a can of cola, you'll see that phosphoric acid is listed as one of the main ingredients. And the sour taste of it is actually what knocks out the sweetness of the crazy amount of sugar that they put in cola. It's some like 3-4 tablespoons or something ridiculous like that. I can't remember the exact quantity. It's insane. So acids actually have a sour taste. That's why vinegar tastes sour, right? So we'll put a hydrogen there, 1, 2, and 1 there. So there's your phosphoric acid molecule. And round 1, it's going to let go of a proton. It'll still have 2 left to give. There we go. So we got that there. 1, 2, 3, 4 oxygens. So that first oxygen is where that negative is from, because that one's sharing a hydrogen and that one's sharing the hydrogen. So that's the H2. So there's that first proton that got released. And if that one releases the next one, off we go to hydrogen phosphate, which we didn't even put on the list. I just put phosphate. But we can deduce that these other 2 animals exist as well. You just don't see them that often. Where do the protons go? All right. So if a proton is a hydrogen nucleus, we just remember, that wants 2 electrons. And then it'll have a full outer shell. Well, here's the crazy thing about water. If I draw a Lewis dot diagram of water, it's got 2 different kinds of electron pairs. Now, let me just kind of shrink that down a bit there. Okay, so these dudes here are called lone pairs. Lone pairs of electrons. And these dudes here are called bonding pairs, because, well, they're bonding. So hydrogen proton, or hydrogen nucleus, or proton, wants 2 electrons. Well, this little proton sees that, and it can actually land on one of those water molecules, which indeed it does for a time, until it can find a better chemical to land on. So now you're going to actually get that proton, and maybe what I'll do is draw that one in gray, like that. So you see that that's the proton. And what it's going to do is it's going to borrow a lone pair of electrons. So what's happened then is that's conferred a positive charge on that thing. And that ion, which has the chemical formula H3O+, is what we call the hydronium ion. But we're not going to really worry about that, but that's actually where they end up most of the time. Now, another weird thing can happen with water. Water itself can actually act as an acid. And if we remember the definition that I just said, an acid is any chemical that can release protons. So sometimes, in your giant solution, when you've got ammonia. Now, ammonia is a molecule with nitrogen in it, with a lone pair. And since nitrogen wants to gain 3 electrons and hydrogen wants to gain 1, we see this pattern here. So we're going to go H2O molecule, and it's going to react with this ammonia group here. And one of these protons, or what's going to happen is water is going to kick this proton and say, you know what, actually, let's do the other one, because then it'll just lay out nicer. Get out, says. So what happens is this proton says, hey, ammonia, can I hang out with you over there? And ammonia says, sure. You can borrow my lone pair there for a little while. And so what's going to happen is then we get our hydroxide ion. So we've got our lone pairs. And I'm just going to draw that electron. that got ripped off from that one hydrogen in gray, so it stands out. Okay, so now that's an ion, and we say that's a hydroxide ion, and we can just write that as OH minus in our chemical equation over here. And obviously then that's going to form the ammonium ion, and that's where the ammonium comes from. So that's why it's a bit weird and it doesn't fit the oxyacid deal. And I'll draw that one in gray just so that you can follow and track that it came from the water molecule originally. Right? So now that thing is a positive charge because ammonia gained a proton. So ammonia acted as a base, we say. So when a substance releases protons into solution, it's acting as an acid, or it's an acid. And when a substance accepts protons, it's acting as a base. The other definition of a base is any substance that dissolves and releases hydroxide ions. Okay? So let's zoom out. We'll see that pattern there. So if we take a look at it here, water is a molecule. Oop, my handwriting's going. It's late. Molecule. That one's a molecule. But when a proton gets transferred, that generated the hydroxide anion and the ammonium cation. And this is why ammonium is a cation. Because it was an ammonium molecule originally that picked up a proton. So now it's positively charged. But there's no metals involved because, well, we started with molecules. So my hope is that this video has explained all this, and I will paste this note into your binder so that you have access to it. You can kind of follow along and see where it all came from. And this is where those polyatomics came from originally.